Hello. So what are your numbers?
What?
What are your numbers?
For what?
Did you read the Google Classroom? Well, you read the Google Classroom. You're in the meeting.
Oh, how many nukes? I didn't see that part. Oof.
You didn't see that part. We just
Only saw the link and I was like, oof, there's the link.
reading with
What part? What? I'm so confused.
Oh, wait. How
What
many?
number? What do you mean by number?
Look at Google
read the
Classroom.
Google Classroom.
And do I have to send a draft? I already sent the essay.
Yeah, that counts as the draft. I'll get that back to you.
Wait, what? I thought
We
there's
need to
no
send-
draft for the essay.
I do need a draft of some sort.
So
doesn't
like,
need- It doesn't need to be spectacular. I just need to know that you have an idea.
oh, so
Can
do we?
you make another post of it though?
Yeah.
But if we don't need to send a draft, can we just like send it right away?
Normally what you do with a draft is you hand in, I will check it and I will send it back to you. And then you re-edit it and send it in again on the same format. It's fine.
Wait,
It'll
I'm in
work.
Google Classroom. What number?
Oh my gosh, Becky.
Essay week for essay 7.
Monday 13. How many nukes have been lost? Have a number ready before we zoom.
Oh.
I'll just post to the chat. MUSJ. And we've changed the number because like they limit you to only 20 meetings. 7837. 7837. 04 2594.
What was that?
Me dying.
Don't die.
Mr. Hendro, everyone eventually dies.
Sorry. Don't die now.
I'll think about
What he
that.
really means by that is please die.
Okay, bye. It was a nice life.
No, it wasn't yet though.
Mr. Hendro, is
Exposing
today
me.
a mandatory Zoom?
Yes, this is an attendance day.
Shorem,
Whoa.
Shorem.
Let me just
Did you
admit
know
it.
that I love you, Shorem?
That's
Yeah,
it.
you won't text me back.
Oh,
What do you mean?
bro,
I text
ignore
you
him. Yedam ghosts everyone. She ghosts me 16 times already.
I think she's
Nothing.
bored.
Why are you counting?
Yedam, I need to
You
count.
know, that's how
every
hurt
20.
we are.
Exactly. See, you're speaking the truth. Yedam.
Start being more considerate.
Yes.
Oh.
Yedam, you're unappreciating your friends.
Yes, I feel very left out.
Yes.
Okay. So, what are your numbers? Just open up the chat section, please type in a number. And by that, it should be on the Google Classroom. You need to open up Google Classroom and read what the question for today is.
Chat. US 6.
Ooh, someone's been reading.
I looked up.
Wait, how do you find the number?
You don't have, it's a guess. How many nuclear weapons do you think the US has lost?
Oh, US?
Oh,
only the
in the
US?
world.
You
In
didn't
the
say
world. In the
UA.
world.
I'll say 40.
You'll say 40?
Yes.
Lost as in like gone missing or
Yep.
like
Gone missing.
Wait, no, I'll just say like 200 or something.
Really?
I mean,
Does that make you feel particularly safe?
no, but I don't think they're gonna directly accidentally send it to Indonesia.
You never
Who
know.
knows, Jonathan? Who knows?
I currently do not have coronavirus. In fact, I only know two people that have had it, and in the whole number of people that I know, and it's still causing havoc on the world.
That's
I
because
can't imagine
people
what a nuclear
are.
weapon would do.
It's because people aren't very What is it?
yes,
Never
John?
mind. It's kind of offensive.
So right now, if I'm not wrong, the coronavirus death toll is over 100,000. That's about either Hiroshima or Nagasaki. That's one nuke.
Oof.
Yeah, and we haven't had infrastructure damage. So if you're going for those numbers, it's kind of insane.
Mm-hmm.
I'll just link in here. There's a link to it's just one web article that you can read that says that there's more than 10. I mean, even one missing nuclear weapon would cause me concern, but this one says that there's 32 that are missing from the US arsenal. This is not including the Kursk, I don't think. There's a lot missing. And it's terrifying. To add to the crazy, I'm going to just show you a quick video. Yeah, I want to show you. It's one of the ones on. This is when nuclear missiles. This is on the. This is
a Minuteman III missile.
No, it's not.
Carrying up
Don't.
to 3 thermonuclear warheads. They
range from 3 to 500 kilograms.
Okay. So this is going to be a quick video about what the US uses for their nuclear weapons program. In terms of their software, remember that most of this stuff was made in the 60s and 70s. So if you think about the 60s, 70s, 80s, cutting edge technology at the time. But think about a car that's 40 years old, 50 years old. Would you drive a car that's 60 years old?
Yeah, that'd be cool.
How often do they break down, Jonathan?
I mean, if it was perfect condition, I don't know.
Are you sure they're in perfect condition? Have a quick look.
This is a Minuteman III missile, capable of carrying up to 3 thermonuclear warheads. They range from 3 to 500 kilotons. That's more powerful than 600 million pounds of dynamite. And this is a cutting-edge computer from the early 1990s, and is used as the system processor to launch the Minuteman III intercontinental ballistic missiles.
This is how we would conduct nuclear war on 8-inch floppy disks.
This is an 8-inch floppy disk. It holds just under 250 kilobytes. It's only good for text documents, a super low-res photo, or a song. Right now, there are over 450 Minuteman III missiles buried deep under the fields in the sparsely inhabited regions of the United States. They're connected by a spider web of thousands of miles of cables, ready to strike at top-secret targets faster than you can get a pizza. Welcome to F.E. Warren Air Force Base, home of the 90th Missile Wing. They command 150 of these Minuteman III missiles.
It's hard to imagine a weapon system more powerful than the one we operate.
And yet, these missiles, their launch control centers, and their command capsules all operate on this antiquated technology.
That processor that it uses to basically run the operating system is about a 386 equivalent. So you're looking at early 90s technology. There is a cursor. It's a square, like an old Atari 2600. We use a trackball, not a mouse. And it has 100 megabytes of hard drive memory, and it has about 16 megabytes of RAM. The missile itself, that guidance computer, uses an operating system about the size of the 8-inch floppy disk. It's about 200 kilobytes of memory. So this is the old 8-inch floppy disk. One channel of communication uses that floppy disk to tell the system how to operate.
It was cutting-edge technology back in 1971.
Old technology is not necessarily a bad thing. With an older weapon system like the Minuteman III, which really was designed in the late 60s to early 70s, it still works, and it provides us some good benefits. Let's leave it in place and not mess with it.
There are benefits to old technology. Modern networked computers can be more easily hacked and compromised with malware, and with these machines, that's more difficult.
We don't use modern technologies. I say modern. Wi-Fi. Wi-Fi's been around for decades. Wi-Fi, Bluetooth. There's no cloud for the Minuteman III operating weapon system. We don't use those technologies, and that gives us a lot of security in that because it reduces the number of vulnerabilities we have. To say anything is hacker-proof, absolutely 100%, that's dangerous. And we would never say that we are 100% hacker-proof. We take a great amount of effort to ensure that we are mitigating every potential vulnerability that we can identify.
While these computers may be from the 70s, the missileers who run these facilities skew a bit younger. Most of them are too young to remember the floppy disk at all, not to mention Pac-Man or Pong. In fact, the disks they're handling are, in some cases, older than they are. The missileers look for false alarms and fake intruder signals caused by stray deer and bad weather. The combination of old technology and humans is what has kept the Minuteman III safe so far.
They're old, and we know that. A lot of the obscure technology that we use still works. So if we don't need to upgrade it, then we don't. With the Minuteman III weapon system, because it is so important and so vital, and the destructive power of the weapon system is so vast, above and beyond anything else, we need to ensure that this weapon system is safe and secure. And I can tell you right off the bat that I have absolute confidence in the safety and security of our weapon system and the nuclear weapons that we use on the weapon system.
So although these machines might be antiquated, this is still arguably one of the most powerfully impactful computer systems in human history. So any changes they're going to make will have to be really well thought out and top secret.
For more science documentaries,
I have absolute confidence in our weapon systems, and they've lost 32 of them. And they're running them off DOS and floppy disks. Okay, so that's basically the intro I'm going to give to this week. I know some of you have done the essay, and at least 3 of you have done the essay. So good job. For those of you who have done it, I will be giving your draft back for that. This week, all I really want you to do is to consider, you don't have to put this in your essay, but just consider the possibility that just even having a nuclear weapon is a problem. There was somebody that gave a quote of, it's quite reasonable for someone to walk a tightrope across Niagara Falls. It's completely unreasonable to expect them to stay on that tightrope for 200 years. It's only a matter of time before something bad happens to one of these. So the closest that I know that you've had to a accidental nuclear detonation on US soil is the Titan II missile disaster in the 1980s. And that's in the Google Classroom. So over the next week, just watch that, hand in the essay. That's it. Okay. For Wednesday and Friday, I will be having the Zoom. You can come in and have a chat with me, but this week is basically an essay week for you guys. I'm giving you a lot of free time to work on that. Any questions?
For the draft you were talking about earlier, so do we just when do we need to turn in the quote-unquote draft that you were talking about?
Wednesday. Now I know you can hand in.
Okay.
I know you can hand in 2 files for your assignment. You're not limited to 1 file. Just label one of them draft. Or if you've already handed it in.
Okay. So you don't need to have a draft if you finished it before Wednesday.
That is your draft. If you finished it, do you
Like
know?
like if you're so what if you're like completely sure you're like done and you're perfect with your essay?
Yeah, I highly.
Whoa.
Look, I'm not going to force you to do it. I won't force you to do it again yet. I won't force you.
Yeah. Okay.
However, what I will say to you is that a draft process is you should do a complete work and then you leave it and you reread it again. Normally based on the number of pages. So if you do 1 page, leave it for a day and then check it again. If it's 2 pages, leave it 2 days and then check it again after 2 days.
So are you gonna read it and give it back to us to edit?
That's the idea.
Okay.
Okay.
That's going to be my holding pattern tomorrow during parent-teacher conference. It's what I do most years. I am also really wanting to drop the exam at the end of the year if I can. But to replace that, I would love to change it to a video presentation that each of you do.
Oh no.
Actually, no.
Actually, please keep the exam. Please don't take it out.
I would rather do the video.
Well, I can't take you guys to Borobudur. We can't do the Borobudur trip. So if it's going to be a capstone project for everything you've done over the last 2 years, just hear me out on the idea here. What sort of, so how many of you have heard of George Santayana? He's the guy that said, those who don't remember history are doomed to repeat it.
The dude you always talk about once in a while.
No, I barely talk about George Santayana. No. He's got 2 good quotes historically about concerning history. One is the one that if you don't pay attention to history, you're doomed to repeat it. And the other one is, history is a pack of lies told by people who weren't there.
Yeah, you said that quote once, like quite often. I didn't know it before
last week.
No way, I heard it. I heard you say it. I swear I did. I swear I did.
Are you okay?
All right.
No, I swear I did.
Just tell me who I'm missing so I can mark you down as absent or not, and you can go.
Kyle.
I think that's yeah.
Doesn't he get an excuse because he's in America and it's like
and like the time difference?
It's actually 12 o'clock at midnight.
Yes. So for those people that are not able to attend, can you, when I post the Zoom on the Google Classroom, can you just write underneath that you saw it for the Hargrave and the Patrick?
Yes.
Lucy, you don't have to come to physical science at the end of the day. Get some sleep. Oh wait, you're still here.
Yeah.
Oh, okay. Come to science at the end of the day.
No, it's Andrew. I don't have to.
I mean, what time are you leaving tomorrow, Lucy?
2:30. But we're like, I have to do last minute stuff. So I don't know if we have a Zoom for science tomorrow, but I won't be able to make it if we do.
No. There's no videos tomorrow. Our videos are on Wednesday, and you're not going to be here, are you?
Wait, do we have a science Zoom today?
Yes, we do, but I'm not going to make Lucy come to it. And I would expect then that you guys should probably say goodbye to her now.
We already said goodbye.
What?
Yeah. So.
Yeah.
It was so annoying coming to your house yesterday and not being able to shake hands or high five or give your dad a hug. It was really annoying.
Well, we'll be back in like 8 months.
Yeah,
7
Mr.
months.
Joe, calm down.
It's just almost a year.
It's okay.
So, Mr. Hendro, I thought you were gonna do like a recap thing, cause something
Recap
of stuff I missed out.
Oh no.
No? Okay.
No.
Okay.
So you're lucky you missed everything.
You can watch you can watch the recap.
Wait, so who won?
I mean,
Can we please not go there?
Humanity
Please.
won. By the grace of God, we're all still alive.
So everyone,
Except Erin.
everyone
I mean,
was fine?
the
Sorry, what's
US would have gotten a
Guys, let's not talk about it.
Yes,
Elsa,
let's just leave it as
if
it
you're
is.
really
You can
curious,
watch the
you can go
video.
watch the recap.
Yeah, you may watch the video.
That's a really long video.
Well,
It's
play
not
it
even
at
15 minutes.
Really? I didn't
It's
check.
very
I'm just
short
a
because like we didn't video it for like the past 5 hours or something.
So, Elsa, basically, we didn't video call at all during the thing. We did a video call at the end, and that's the only thing that's the recap.
Oh, okay.
There are actually 2 recaps, one from the day and one from the Zoom app and from the end of the week after that.
So, Mr. Hendro, for science Zoom, are we like just talking, or like what are we gonna do in science Zoom?
I am going to be looking at a really weird phenomenon where the inside of an object has no charge. So not no charge, but there's no electric field inside an object. And how to exploit that.
Okay.
So we're gonna exploit not a Van de Graaff, but the opposite of a Van de Graaff. Actually, no, it is a Van de Graaff. But I want to use a paint can or some sort of tin instead. We'll be, instead of moving the charge from the Van de Graaff out to zap people, we'll move charge into the Van de Graaff.
So unzaps people?
No, but we'll have a look at it. We'll have a look at what we can do on the morrow.
History class.
So we have 2 units left for science. The 2 units left for science. Do you want to just do it now and get it out of the way? Do you want to just do the science thing now so that it's out of the way?
How much more time do we have on Zoom?
Let's go.
We have another half an hour-ish.
How much more time until 5th period?
30 minutes.
30 minutes? Half an hour? It's 30
I mean,
minutes.
if everyone's good with it, then let's just do it now.
All right. So if you've got chapter 33, there. It's electric fields and electric potential. So one thing that I find really, really interesting is this picture on page 520. This is the bit that I really want you guys to be looking at. Have you got that page? Have you got that page open? Can I just have a thumbs up thing on your little faces?
What page?
Page what?
Page 520.
Yes.
520. So you got that image? Okay, good. I'm seeing a bunch of thumbs up.
Yes,
Excellent.
I have it.
Okay, so if you have those thumbs up, great. What you're seeing there is the phenomenon of field lines, and you'll notice that on the points, the point charges, the pictures A and B, they radiate directly away from the point charge. You will notice on pictures C and D, on the bars have these, at the end they have it radiating outward, but on the flat edges it goes directly away. We kind of saw this on the Van de Graaff experiment that we did. However, what I would really, really like you to see is the field in picture C. The field in picture C is especially useful because it's in a straight line. What happens if the bar on the left is negative and the bar on the right is positive?
They will attract.
Well, yes, but they're not moving. So I have two bars. Is that going to be thick enough? No. Draw another one here. So you have two bars here. If one of these is positive, can I just do drawing? Squigglies? If this is negative, if this is negative, why can I not draw? Okay, so if you have a negative and a positively charged plate here, your field lines are going to be in one direction. So your field lines are going to be going, let's just say that the electrons, actually no, the electrons won't want to move there. The electrons will want to move in this direction. That is the way the electrons will want to move. And it's really useful to have this particular setup because this basically mimics a gravitational field. Now, do you remember potential energy?
Yeah.
You remember potential energy? You had, let me just change the color here. On potential energy, you had E. And potential energy, you had a ground, you had the ground, and you might have had, I'm just going to draw this so people know that it's, that I'm trying to draw a tree. Okay. If you have an object that's put on a, you have a gravitational field here. So the gravitational field is downwards in this direction. Now, that field is constant along the whole thing. The same way that the field between these two plates is the same. Now, if I was to get a block and I was to put it here, how do I determine how much is this thing's potential energy? That's horrible. Let me just change that color to something that's more blockish. There we go. There you go. You have a block there. What is this thing's potential energy?
Isn't it something like weight divided by height or something?
Ooh, weight. What determines weight? Weight is a force.
Huh?
Weight
Gravity.
The mass.
M times G.
Go on, annotate. Try writing down. Okay, mass times G equals weight. And so it's the same in the whole thing. So this is the downward force. Weight is a force. But we're not looking for force. I'm looking for the potential energy. What would be the potential energy?
Wait, potential energy of the block?
Yeah, let me just compare this. So this is, let's just call this, yeah, let's call this thing block 1. That's block 1. Now I'm going to give you another block up here. I'm going to give you a block up here. I'll give that block 2. Which of those two blocks has more potential energy? They're the same size, same mass, same gravitational field. Why is the top one?
Because it's higher up.
Right. So your potential energy has to do with, I'll get rid of this completely if I can. How do I erase? Ooh, that got rid of too much. Anyway, so your potential energy has to do with, come on. That's a hard one. Mass times gravity times height. Can I change that to a better color? There you go. So that's your potential energy. What would you do in an electric field? This is in a this over here is in a gravitational field. What happens in an electric field? If I was to drop a little point charge, a tiny little point charge, just here, and that's going to be yellow again. I don't want yellow. Let's make it red. I drop a tiny little point charge here. I'll put another point charge here. Okay? And I will draw this one to be a negative charge and this one to be a positive charge. Which one has the greater potential energy?
The positive one, maybe?
Why? Which way will the positive charge move?
Wait, doesn't like positive and positive doesn't attract, so it just goes
Yes,
out?
so the
But
positive's going to go, the positive charge is going to go this way.
wait,
So let's get that all the way to the plate. It'll travel all the way to the plate. You've got one photon there. And you have this negative charge is going to travel all the way there. Okay? So which one has the greater potential energy?
Negative.
Which one?
The negative?
The negative has the greater potential energy, and not assuming that the mass is not there. But the distance that it travels will have a great effect on the amount of potential energy that it has. This is why when you create a capacitor, the separation between the two plates that you use needs to be at a certain distance. Now, this is very useful if you wanted to, say, store static electricity for like what's a use that you might be able to understand? Like to flatten out the peaks on a waveform. So if you want to turn something from alternating current to direct current, you could use this technique. So you can see this kind of field between plates, and you can see this in figure. You can see this in figure. You can see this in figure C on page 520. The other figure that I'd like you to look at is figure D. This is the weird one. Look inside the circle. What is the electric field?
It's completely still?
There is no electric field inside there. It's not a magnetic field, it's an electric field. There's a difference. If you are getting hit by lightning on the outside of your car, because the car is completely enclosed, there is no electric field. So the potential difference outside and inside doesn't matter. The lightning will hit the top of the car, go around the car, and zap out the bottom. This is called a Faraday cage. So this is particularly useful.
Wouldn't it still damage your car?
Yes, on the outside. But the purpose of having a car that can survive a lightning strike, which is why you close your windows during a lightning storm, you don't open them, is so that none of the electricity gets inside the car. All right. They've actually got a picture of a car getting hit by lightning on page 521 if you want to have a look there. I have no idea if that car had a problem afterwards, but I'm pretty sure the people inside would have been okay. So,
I have a question.
Just a minute. I'm assuming most of you don't have a multimeter at home, do you?
No.
No.
Okay. What was your question, Dylan?
So do we switch science to now so we don't have science later?
Yeah, I don't want to do science later.
Lazy.
Very nice.
Means we can get this done and I can hand out your so there's 3 things I want to do for this week. A test, a set of questions in a lab.
Wait, a science test?
Yeah, science test, a set of homework questions, and a lab. And
when would this test be?
I might actually get it done early so you have a whole week to do it in.
Mr. Hendro, Mine might be a little bit late because I am going to be traveling for like the next 4 days.
Ugh.
You could study in that 4 days.
No.
Yeah, so
No. You want to be watching Disney musical if you're stuck in a plane. I mean, of course, if that's what you.
well, I
There's a kid screaming like the whole flight next to you.
oh joy.
Yep. I hope you get to sit next to Hannah instead of Evan.
I don't want to sit next to either of them.
Good.
Well, they've both got their flaws.
Okay, so we're going to be still working with electric field lines for the experiment. The experiment I'm going to do is going to be similar to the Van de Graaff experiment in that there will be a Van de Graaff shell, but that shell is going to be inverted. It's going to be an upside down painting. Now it's going to be almost exactly the same as this particular shape in that it's going to be a circle. So what should happen inside this cage is that there should not be any electrical charge. And I'm still hoping to survive this. Don't laugh. What I hope to do is be able to take a charge from a power outlet somehow. So that'd be 220 volts of potential.
What the heck? No, Mr. Hen.
No. Static charge. So the charge will charge a conductive material, which will be separated by an insulator. And then I move the charge from the electrical outlet onto the Van de Graaff. What I want to see is what's the difference between putting the charge on the outside and putting the charge on the inside. It's not dangerous, Jonathan, because there is going to be almost no charge. Your potential difference is different from the energy involved. Here, let's go back to that. Let's go back to that whiteboard again. So while the amount of force that's being applied, the potential difference on the negative particle is much larger. If you count the amount of mass there, it's almost nothing. If I was to drop a grain of sand from the top of the library onto my foot, it's not going to do much. If I drop a table onto my foot from an inch above it, it's still going to have a lot more energy. So what you're doing from a power point, as in like an electrical outlet, that 220 volts is almost nothing if you're only counting a few million electrons on the surface instead of a few, quadrillion electrons. A few quadrillion electrons traveling at the same time is deadly. But a million or so, you hardly feel it. It's like, the potential difference on the surface of your skin. If it's that small, you'll feel the zap, but it's not going to damage you. Does that make sense? It is almost as though if you were to change this equation here, your potential difference due to voltage, it's once again relative to the distance, but what you have is you have the charge Q. Is it charge Q? One volt is joule per coulomb. You have the charge of electrical potential energy has to do with distance. Sorry, just give me a second. I want to have a look at not Coulomb's law. It's not voltage. Electrical potential energy. Energy formula, which was distance between electrical potential, Coulomb constant, charges. Okay, so it's just a constant. Oh, that has to do with the material in between. Okay, that makes sense. Okay, so there is a constant there, but it's basically the charge divided by the distance. That can't be right. The more the distance, the greater the voltage. So why is it? Oh, okay. So that's that. That's wrong. All right. Okay. Okay. So that's the difference between the potential of the electrical potential energy. Yeah. Okay. P electric. So electrical potential energy is different from voltage, and that's an inverse. That's an inverse relationship. Okay. That's an inverse relationship there. It should come out as joule per coulomb. Really? Doesn't quite make sense. Get rid of that last bit. Why is that not getting rid of? Why is my annotations not working? Why is my annotations not working? More annotations. Where are the annotations? Ay, 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 ay. Why can't I access my annotations? Meeting controls. Or why are you not giving me my annotations? Stop share. Stop share. Let's try that share again. There we go. Great. Okay. So your potential electrical is equal to a constant multiplied by the square of the charge over the distance. So we're going to assume that there's a constant multiplied by, let's talk a big charge and a small charge, and then you divide that by the distance between them. So that constant probably has to do with, it's not that constant, is it? We're not going to talk about dielectrics. So you're not going to be talking about capacitors in between this. Do they talk about capacitors next chapter? Electric current, electric resistance. Next chapter, Ohm's law. Charge current resistance for electric shock. Alternating current. Oh, they do talk about a diode. All right, so we don't actually cover capacitors. That's interesting. Why don't they cover capacitors? And electricals. Oh, they do cover capacitors. Okay, so it's this chapter that we actually do cover capacitors. Interesting. All right, wonderful. So what we're going to do for the experiment is we're going to try to using our understanding of the way these currents, these equations work. So if you have this difference in charge across an electric field, what happens when you eventually move this? If I tried to move this current towards there, you would induce an electric field on the surface. If you finally induce an electric field on the surface that you're trying to move the current to from the outside, it shouldn't work. But if you have this condition where the inside of your Van de Graaff is constantly, if the inside of your Van de Graaff is constantly empty, then your potential difference should always be the same because your Q values should always be different. Does that make sense?
No.
No, all right.
No.
All right, well, I will expound on that later. For the moment, though, I will get you some questions to be doing because we have a question, an experiment, and a test in the next 2 weeks. Okay? That's the basic
What's
outline.
after the 2 weeks?
After the 2 weeks, we're going to go into current because at the moment we're just talking about statics. So the electricity is not moving anywhere. If I put electricity into an object, it stays there. Okay, we're not talking about flowing electrics yet. Okay.
For the questions, can you post it on Google Classroom? So
Yes.
what
I actually
questions?
have them,
Okay.
I have them right in front of me here. I will get them up to you shortly.
Okay, thank you.
Do you have the book with you, Hargrave? I mean, Lucy.
I took pictures of everything you told me to.
Okay, so chapters 33, 34.
Yes, sir.
That should do it.
Okay,
right.
thank you.
Thank you, ladies and gentlemen.
Goodbye.
Okay, see you guys later.
Thank you, Mr. Andrew.
Thank you, Mr. Andrew.
Thank you.